Hello everyone! When you were little, you probably believed in the freshman's dream, this equality. This is a great example of something too good to be true, since in reality, this expression equals something much more complicated, hence the name freshman's dream. In this video, we'll explore another equality, one between this integral and this sum. So beautiful, isn't it? There are so many fascinating implications about this result, and it feels too good to be true as well. Well, it turns out that this equality, referred to as the sophomore's dream, is correct. Let us understand why. The function we want to integrate does not have an elementary antiderivative. Even computer algebra systems don't show any kind of result. So here we have to get a bit creative and not rely on the evaluation theorem. Well, good things often happen in calculus when we introduce the constant e. So how about we rewrite our integrand as e raised to some logarithm? For example, e to the log of x to the minus x. Here the exponent and the logarithm cancel each other out. We can then use our properties of logarithms to write the exponent as minus x times the log of x. And really the whole point of using e here is so that we could use our good friend, the Maclaurin series, for the exponential function. Recall the Maclaurin series e to the x, which is this sum from 0 to infinity with n as the index of x to the n over n factorial. We can simply substitute this into the integral because this sum is convergent for all values of x. We can rewrite our integrand now as a sum and get that this is the same as the integral from 0 to 1 of the sum from 0 to infinity, and then simply substituting this input into this series. So we will get minus x times the log of x to the n over n factorial in dx, of course. And because this series is absolutely convergent on our bounds of integration, we can simply integrate term by term, or equivalently swap the integral and the summation sign. And so we can get that it is equivalent to the sum from 0 to infinity of the integral from 0 to 1 of this function, minus x times ln of x to the n over n factorial dx. In reality, this swapping is not that simple. There's a bit higher logic to it, but I won't get into that in the video. If you know, please leave a comment. Anyways, we can keep going and take out some constant terms our integral and put it in front of the sum, and we can get a final result of the sum from 0 to infinity, taking out the negative 1 to the n and the factorial, and then we are left with the integral from 0 to 1 of a bit simplified function x to the n times ln of x to the n in dx. So we essentially reduced our integral from the start into another integral from 0 to 1. However, this one can be done with a very interesting trick involving the gamma function. Let's take a look at it. Let us recall the definition of the gamma function. It is defined as this improper integral, and it is also known as the extension of the factorial function into all complex numbers. As you're about to see, we can use this function to help evaluate the integral we want to, or rather we can convert our integral into a form of the gamma function. To start integration, we have to consider our bounds. The integral we want has the bounds from 0 to 1, but the gamma function has the bounds from 0 to infinity. So how would we possibly convert to that? Well, how else would we change our bounds but by substitution? So is there some substitution that could change these bounds into infinite ones and not from 0 to 1? Look at this. Let's have some new variable, let's say u, equal to the negative logarithm of x. It is right here in our function, the logarithm, just negative. Then we can differentiate it to get that du is equal to negative 1 over x dx, such that dx is equal to negative x du. And notice our bounds, how they will change. The logarithm evaluated at 0, well, it can't be evaluated at 0, but we can consider the limit, and the negative logarithm will soar up to infinity. And its evaluated at 1 will simply be 0. So really, we can now change our integral with the substitution and get that this integral is equal to the integral from infinity to 0 of, and then we can substitute stuff in here. We get x to the n, let's not change it for now. And the logarithm, it's just negative u to the n, and dx is equal to negative x du. So this is our first step. We can do a bit of simplifying later. We can simplify this integral first by noticing that x is equal to e to the negative u. Then we can swap our bounds of integration and take the negative outside to get that this is equal to the negative integral from 0 to infinity. Then this negative u to the n right here, I'm just going to put the negative 1 to the n outside. And then we can make our substitutions with x and get that this is times e to the negative u n, and then times u to the n, and then the negative x just becomes negative e to the u times negative all of this e to the negative u, and this is all in du. We can continue our simplification a bit. Notice there's a negative outside and a negative inside, so those just cancel each other out. And so I would take this negative 1 to the n term outside, and then the rest of the integral will be just the same as e to the negative u n, then times e to the negative u, and then times u to the n in du. And so we can merge these two together, adding up the negative u n and the negative u and factoring to get that this is equal to, wait for it, e to the negative u times n plus 1, and then times u to the n and du. Now this closely resembles our gamma function. Notice our t term right here, which is positive, it resembles the u term right here, u to the n, and notice the e to the negative term here, it also resembles our e to something negative. And we can really clean this up and transform this into a gamma function with one more substitution. We can make one last substitution here for the exponent. Let's have t, for example, equal to u times n plus 1, which is right here. And so we get that dt is equal to n plus 1 du. And so we get the result of minus 1 to the n times the integral from 0 to infinity of e to the minus t. Oh, look at that. That's determined our gamma function. And then u to the n. Well, u is just equal to t over n plus 1. So it's just times t over n plus 1 to the n. And then du, that's just equal to dt over n plus 1. So dt over n plus 1. And finally, by taking all of the n terms outside, we get here, you see n plus 1 to the n, but then it's times n plus 1 again. So really outside it should be n plus 1 to the power of n plus 1. And inside we have our lovely gamma function, the integral from 0 to infinity of e to the minus t, and then times t to the n in dt. How nice is this? When you look at this, this is really just gamma of n plus 1, according to our definition. So really this is equal to then minus 1 to the n over n plus 1 times, no, to the power of n plus 1, and then times the gamma function of n plus 1. The hard part's done. We can now put this answer into our sum to get the sum from 0 to infinity of minus 1 to the n over n factorial, and then times this, times another minus 1 to the n over n plus 1 times to the n plus 1, and then times the gamma function, gamma of n plus 1. But we know that the gamma function is just an extension of the factorial function to the complex numbers. But here, n is a natural number. That means the gamma function is equivalent to the factorial in this summation. Therefore, we can simplify this to n factorial. And look at that, the factorial in the denominator, the factorial in the numerator, they both cancel out. Just as the negatives 1 to the n, that becomes negative 1 to the 2n, which is always 1. And so we simply get a sum from 0 to infinity. And even here, we can simplify the index. The 0 here, the n plus 1's here. We can just make the index 1 and remove the 1's from each of these. Just a lot of simplification that's very evident to see. So with our index of 1, still going to infinity, 1 over n to the n. When you look at that, that's the same as the sum from 1 to infinity of n to the minus n. How beautiful is that? We have shown the Sophomore's dream identity between this integral and this infinite sum. The series we just equated this integral to is convergent. You can easily verify this with the ratio test or a direct comparison to a p-series, for example, and it has a value approximately equal to 1.29, which is pretty cool. Now there's also an integral that we can solve very related to the one we just did of x to the positive x. We can do the same, the Maclaurin series expansion for the e to the x, and then we can get this integral again, which we evaluated to be equal to this times the gamma function. Stuff cancels out and we get another series. It's very similar to this one, but it is alternating. And by the alternating series test, this also converges and about to a value of 0.78. And that just about wraps up our video on the sophomore's dream identities. That's right, the sophomore's dream is not just the first identity, but also the second one. Well, it's not like the name has much importance, right? There's not an application to this result at all. It's just an aesthetically pleasing result. But that's what math really is about, isn't it? Okay, so thank you all for watching, and I will see you in the next video.